the topic we are going to discuss is differentiation of inverse trigonometrical functions. We have already studied inverse trigonometrical functions. Now, before taking up the differentiation of inverse trigonometrical functions, I will very briefly discuss what we have studied in inverse trigonometrical functions. Now, all these inverse trigonometrical functions are multi-valued functions. All these functions are multiple valued functions. What does this mean? For example, say sine inverse 1 by root 2. What is the value of sine inverse 1 by root 2? Let sine inverse 1 by root 2 be equal to theta. That this implies 1 by root 2 is equal to sine theta. Now sine theta is positive. So sine theta is positive in which quadrant? Sine theta is positive in this quadrant and this quadrant. So this implies, and value of sine theta is 1 by root 2. So value of sine is 1 by root 2 at theta equal to pi by 4 at 45 degrees. So theta will be equal to pi by 4 if we take the value in this quadrant. But sine theta is also equal to 1 by root 2 at pi minus pi by 4. In this quadrant, sine is positive, so pi minus pi by 4. Sine of pi minus pi by 4 will be equal to sine of pi by 4. So again the value will be 1 by root 2. Or we can again consider it will be 2 pi plus pi by 4. In this quadrant again we can take the value as 2 pi plus pi by 4. Sine of 2 pi plus pi by 4. 2 pi is even multiple, so sine will remain sine. And we will have sine 2 pi plus pi by 4 is equal to sine of pi by 4. Sine of 2 pi plus pi by 4 is equal to sine of pi by 4. So value will again be 1 by root 2. So on. This implies theta is equal to pi by 4 or 3 pi by 4 or 9 pi by 4 and so on. Therefore, sine inverse 1 by root 2 can have the values pi by 4. It can have the value 3 pi by 4, 9 pi by 4. So what we see is at each point of the domain of sine inverse, it has more than one values. Now in order to make this function a single valued function, we consider the principal branch. We consider the principal branch. In this branch, at each value of x, the function will have only one values. The multiple values will be deleted. So in principal branch, at each value of the domain, we will have a unique value in the range. For this branch, at each point of the domain, we will have a unique value of sine inverse at that point. At each and every point of the domain, we will have a unique value in the range. Now, first is sine inverse x. Sine inverse x. Domain of sine inverse x is same as the range of sine x by definition of inverse functions. Domain of sine inverse x is same as the range of sine x. Now, range of sine x, values of sine x lie between -1 and 1. All the values of sine x must lie between -1 and 1. So, range of sine x is domain of sine inverse x. Cos inverse x. Now, range of cos inverse x is again minus 1 to 1. Range of tan x, values of tan x lie between minus infinity to infinity, whole real line. Tan of pi by 2 is infinity and tangent of minus pi by 2 is minus infinity. So the values of tangent lie in the whole real line. So range is whole real line. So domain of tan inverse x will be whole real line. Cot inverse x. For cotangent, again range is whole real line. Cotangent of 0 is infinity. And cotangent of pi is minus infinity. So secant inverse x. Secant inverse x. Now we know mod of secant theta is always greater than equal to 1. Mod of secant theta is always greater than equal to 1. Mod of cos theta is less than equal to 1. So its reciprocal is secant. So mod of secant theta is greater than equal to 1. So range of secant theta is minus infinity to minus 1 union 1 to infinity. The range of secant theta is this, therefore domain of secant inverse is this. Cosecant inverse. Cosecant inverse x. Again, range of cosecant theta is minus infinity to minus 1 union 1 to infinity. Because we know sine of theta is less than equal to 1. That is, values of sine theta lie between minus 1 is less than equal to sine theta is less than equal to 1. And therefore, cosecant is reciprocal of this. So, values of 1 upon mod sine theta will always be greater than equal to 1. That is, mod of cosecant theta is greater than equal to 1. And mod of this is greater than equal to 1 will imply that either cosecant theta is less than equal to minus 1 or cosecant theta is greater than equal to 1. Because we know mod of x is greater than equal to L implies either x is less than minus L, less than equal to minus L, or x is greater than equal to L. This is the standard result. Mod of x is less than equal to L will mean values of x lie between minus L and L. If it is greater than equal to L, the values will not lie between minus L and L. Mod x is less than L. This means the values lie between, this is minus L and this is L. So values will lie between this interval, in this interval. And mod of x is greater than equal to L will mean values do not lie in this interval. So the values will lie here. So mod of x is greater than equal to 1 will mean values do not lie between minus 1 and 1. So values will lie in this interval and this interval. Less than minus 1 and greater than equal to 1. Less than equal to minus 1 and greater than equal to 1. Now we come to the range. Now range of any of these inverse trigonometrical functions does not lie in the third quadrant. Third quadrant does not belong to the range of any of these inverse trigonometrical functions. You can remember this as a golden rule. Third quadrant does not belong to the range of any of these trigonometrical functions. Now if x is positive, this will mean sine inverse x is equal to theta. This implies x is equal to sine theta. Now if x is positive, this will mean sine theta is positive. And sine theta is positive in first quadrant. So if x is positive, value of sine inverse x will lie in first quadrant. And similarly for all other inverse trigonometrical functions, if cos inverse x is equal to theta, then x is cos theta. If x is positive, cos theta will be positive. If x is positive, cos theta will be positive. So positive values will be taken from the first quadrant. If x is positive, then cos inverse x will lie in first quadrant. X is positive, tan inverse will lie in first quadrant. And similarly for others. If x is positive, all these inverse trigonometrical functions will lie in first quadrant. If x is positive, this will lie in first quadrant. X is positive, cotangent inverse will lie in first quadrant. X is positive, secant inverse will lie in this quadrant and in this quadrant. And for negative values, we will take one of these quadrants, either second or fourth. We will now make you understand which quadrant has to be taken. Just remember this and you will not have to memorize the domains and range of inverse trigonometrical functions. Just remember the logic. You will not have to memorize the domain and range of these functions. Now for negative values of x, if x is negative, sine theta will be negative. If x is negative, sine theta will be negative. So sine theta is negative. In this quadrant, sine theta is positive. So we need not consider this quadrant. Only these values will repeat. So for negative x, sine inverse x will lie in this quadrant. So range will be minus pi by 2 to pi by 2. Range will be minus pi by 2 to pi by 2. Cos inverse x. For positive, this will be 0 to pi by 2. When x is negative, cos theta should be negative. Now cos is negative in this quadrant and positive in this quadrant. If I take this quadrant, only the values will get repeated. So positive values will be taken from first quadrant and negative from this quadrant. Third quadrant does not belong to any of the, cos is negative in this, but this does not belong to the range of any of the inverse trigonometrical functions. So range will be 0 to pi. You don't have to memorize. Now I come to secant inverse x. Now secant inverse x. X is positive in first quadrant. And if x is negative, secant theta should be negative. Secant theta is negative. Secant theta is negative in this quadrant and positive in this quadrant. So negative values will be taken from this quadrant. So what we get is range is 0 to pi. But secant is not defined at pi by 2. Secant is not defined at pi by 2. Because cos of pi by 2 is 0 and secant is 1 over cos. So 1 over 0 is not defined. So this point has to be deleted. We will get 0 to pi minus pi by 2. So this will be the range. And for cosecant, positive values from first quadrant and negative. Now cosecant is again positive in this, it is negative in this quadrant. Cosecant is negative in this quadrant. So we will take the range as minus pi by 2 to pi by 2, minus pi by 2 to pi by 2. But cosecant is 1 over sine, and sine is 0 at x equal to 0. Sine is 0 at x equal to 0. So we have to delete this point because cosecant is not defined at x equal to 0. So we will delete 0 to. Now we come to tan inverse x. X is positive, then tangent theta will be positive, and we will take the values from first quadrant. And if x is negative, now tangent is negative in this quadrant as well as this quadrant. In both these quadrants, tangent theta is negative. So which quadrant should we take? Say this quadrant. Then it will be 0 to pi, and we will have to delete pi by 2. But if I take from here minus pi by 2 to pi by 2, the interval is continuous. We don't have to delete any of the points. So what we do is, instead of taking 0 to pi, we will take minus pi by 2 to pi by 2. This is more logical. Minus pi by 2 to pi by 2. Tangent is not defined for this line. At pi by 2, tangent is not defined. At minus pi by 2, it is not defined. But these are the endpoints, and we take the round bracket here. Delete these points, and we get a continuous interval. So we will take the principal branch as this, minus pi by 2 to pi by 2. We will get a continuous interval. And here there was no solution because secant was positive in this and again positive in this. It was negative only in this quadrant. So we have to take this interval and delete this point from the middle. But in this we have either we can take this or this. But in this, pi by 2 is in the middle of the interval and we have to delete it. So we take minus pi by 2 to pi by 2. And for cotangent, cotangent is again negative in this and negative in this. So again we take this. Suppose I take the same interval, minus pi by 2 to pi by 2. But cotangent is not defined for x equal to 0. Cotangent is not defined for theta equal to 0. At 0 it is not defined. So we have to delete this. So either I take minus pi by 2 to pi by 2, then I will have to delete a point in the middle of the interval. What we do is we take 0 to pi. Then we don't have to delete any of the points. Only the end points will be deleted. So we take a round bracket here. So 0 to pi open interval. So what we do is here this will be taken. So here we take continuous interval, minus pi by 2 to pi by 2 and 0 to pi. You must note this. Rest you will not have to memorize anything. So take the most logical interval. Now with this background, I start with the differentiation of inverse trigonometrical function. This logic is only as, may be taken only as aid to memory. This is only aid to memory. These expressions are only as aid to memory. So you don't have to remember the domain and range. Domain is range of the corresponding trigonometrical function. And for range, positive values for all the inverse trigonometrical functions are taken in from the first quadrant. And for negative quadrant, there is only one quadrant in which it is negative. So this is taken. In for cos inverse, it is negative in only this quadrant. So this quadrant is taken. Here it is negative only in this quadrant. Here it is negative only in, so this is taken. But in tan and cotangent, it is negative in two quadrants. in second and fourth. So what we take is, we take minus pi by 2 to pi by 2 because it is not defined for this line. So we delete the endpoints and take this. If I take this, then in the middle of the interval I will have to delete pi by 2. So this is considered the standard principal branch. And here also we have two intervals in which cotangent is negative. So we take a continuous one 0 to pi. With this background, I start with the differentiation of inverse trigonometrical functions. Now I take up the differentiation of first inverse trigonometrical functions, that is sine inverse x. Let y be equal to sine inverse x. Then this implies sine of y is equal to x. Sine of y is x. Now differentiate both sides with respect to x. What we get is d by dx of sine y is equal to d by dx of x. This implies now d by dx of sine. Differentiation of sine is cos. Cos y. Now a formula for x is being used for y. So we must take the differentiation of the inner function, that is y. This must be equal to d by dx of x is 1. And this implies dy by dx is equal to 1 upon cos of y. This implies dy by dx is equal to, now sine square y plus cos square y is 1. So what we have is cos square y is equal to 1 minus sine square y, and therefore cos of y is equal to under the root 1 minus sine square y. So this will be equal to 1 upon under the root 1 minus sine square y. And this implies dy by dx is equal to 1 upon under the root 1 minus sine y is x. From 1 sine y is x. So we get dy by dx is equal to 1 over under root 1 minus x square. Now dy by dx is equal to 1 over under root 1 minus x square. But in this step, we have taken cos square y is 1 minus sine square y, and therefore cos y is equal to under root 1 minus sine square y. But it should be plus minus under root 1 minus sine square y. So why we are taking positive sign here needs an explanation. Now we know that domain of sine inverse x is domain of sine inverse x is equal to, now domain of sine inverse x is range of sine x, and range of sine x is minus 1 to 1. Minus 1, 1. This is the domain of f. And the range of sine inverse x. Now sine inverse x, range of sine inverse x is positive values are taken from first quadrant, and third quadrant does not appear in the range of any of the inverse trigonometrical functions. So we are left with the second and fourth quadrant. In second quadrant, sine is again positive. So we do not consider this because these values will be repeated. Therefore, negative values are taken from the fourth quadrant. Therefore, range of sine inverse x should be minus pi by 2 to pi by 2. Minus pi by 2 to pi by 2. This means, now domain of f. Domain of f is all those x for which this function is defined. So domain means x belongs to minus 1 to 1. And range is the set of values taken by the function at the points of its domain. That is, these are the values taken by this function at the points of its domain. So these are the values of y. Therefore, y belongs to minus pi by 2 to pi by 2. Now y belongs to minus pi by 2 to pi by 2. That is, y belongs to these two quadrants. In these two quadrants, cos y is positive in first quadrant and cos y is positive in fourth quadrant. Therefore, for y belonging to this, cos y is positive, and therefore cos y is positive, and therefore we are taking only plus sign. So differentiation of sine inverse x is 1 over under root 1 minus x square. And differentiation of cos inverse x, you can try yourself. Differentiation of cos inverse x, you can try yourself on similar lines. I take up differentiation of tan inverse x. Let y be equal to tan inverse x. This implies tangent of y is equal to x. Differentiating both sides with respect to x, what we get is d by dx of tan y is equal to d by dx of x. Now d by dx of tan y, differentiation of tangent is secant square y. A formula for x is being used for y. So we take the differentiation of inner function dy by dx. This is equal to 1. Inner function is y. Instead of x we have y, so we must take dy by dx. So we get dy by dx is equal to 1 upon secant square y. Now we know secant square y minus tan square y is equal to 1. Therefore, secant square y is equal to 1 plus tan square y. So we will get 1 upon 1 plus tan square y. But from 1, tangent y is x. Tangent y is x. So we will have 1 upon 1 plus x square. So this is the required differentiation. So we have d by dx of tan inverse x is equal to this much. And on similar lines, you can find the differentiation of cot inverse x. Differentiation of cot inverse x, you can try yourself. I am taking up differentiation of secant inverse x. Now we take up the differentiation of secant inverse x. Let y be equal to secant inverse x. Now domain of f is, now range of secant x is mod x greater than equal to 1. That is minus infinity to minus 1 union 1 to infinity. This is the range of secant x. So domain of secant inverse x will be range of secant x. That is mod of x is greater than equal to 1. And range of f is, now positive values are taken from first quadrant, and this quadrant does not appear in the range of any of the inverse trigonometrical functions. So we are left with the second and third quadrant. Now secant is negative in this quadrant and positive in this quadrant. If I take this quadrant, these values will be repeated. So we take this. So range of f will be 0 to pi, but secant is not defined at pi by 2 because cos pi by 2 is 0 and secant is 1 over cos pi by 2. So this point has to be deleted, minus pi by 2. Or we can write this as 0 to pi by 2 union pi by 2 to pi. This point has to be deleted. You can write it like this, or 0 to pi by 2 union pi by 2 to pi. Now y is equal to secant inverse x. So this implies x is equal to secant of y. X is equal to secant y. Differentiating both sides with respect to x. What we get is differentiation of x is 1, differentiation of secant y is secant y tangent y into dy by dx. And this implies dy by dx is equal to 1 upon secant y tangent y. Now y belongs to this interval. Therefore secant y is not equal to 0 at any of these points. But for tangent y, we must delete the points where tangent y is 0. It should not be 0 because 1 by 0 is not defined. So we must put a restriction here, tangent of y is not equal to 0. This implies y is not equal to, now tangent y is 0. Tangent y is 0 at y equal to 0 and pi. Tangent y. Tangent y is 0 on this line, 0 and pi. So these 2 points have to be deleted. So therefore now y must belong to, this point has been deleted. So 0 to pi by 2 union pi by 2 to pi. This point has been deleted because otherwise tangent y will be 0 and this will not be defined. So the formula for differentiation of secant inverse x will be defined only for y belonging to 0 to pi by 2 union pi by 2 to pi. And y equal to 0. Y equal to 0 will mean secant 0. Y is 0 means secant 0. Secant 0 is 1. So x cannot be equal to 1. X is not equal to 1, and at pi, secant of pi is 1 over cos pi, and cos pi is minus 1. So x is equal to minus 1. So x cannot be equal to 1 or minus 1. So we will have mod x will be greater than 1. Mod x cannot be equal to 1 because mod of minus 1 is 1, mod of 1 is 1. So we will have to delete these 2 points, or we can say the result will be valid only for x belonging to minus infinity to minus 1 open interval union 1 to infinity, or mod x greater than 1. It will not be valid for x equal to plus minus 1. Now we come to the main point. Now case 1. Case 1 is y belongs to 0 to pi by 2. Now y belongs to 0 to pi by 2. That is, y belongs to first quadrant. In first quadrant secant y, therefore secant y is positive and tangent y is also positive in this quadrant. And therefore secant y tangent y is greater than 0. Therefore secant y tangent y is equal to mod of secant y tangent y. Mod of x is equal to x if x is greater than 0. This is greater than 0, so this must be equal to its mod. And case 2, y belongs to 0 to pi by 2 union pi by 2 to pi. Now y belongs to pi by 2, this interval, pi by 2 to pi. So this is which quadrant? This is second quadrant. In second quadrant, secant y is negative and tangent y is also negative. And therefore, secant y tangent y must be greater than 0. Negative into negative is positive. So this must be greater than 0. And therefore, secant y tangent y must be equal to secant y tangent y. So in both these intervals, secant y tangent y is equal to its mod. And therefore I can write 1 as, therefore 1 implies dy by dx is equal to 1 upon secant y tangent y can be written as mod of secant y tangent y. And this is equal to 1 upon mod of secant y mod of tangent y. Now we know mod of x is equal to under root x square. Mod of x is under root x square. So this is equal to 1 upon mod of secant y under root tan square y. Tan square y. 1 upon mod secant y, and this can be written as under root tangent square y. And this is equal to 1 upon mod secant y under root secant square y minus 1. And this is equal to 1 upon, now secant y from this equation is, call this as say A. From this equation, secant y is x. Mod of x under the root secant y is x square minus 1. 1 upon mod x under root x square minus 1. So derivative of secant inverse x is 1 over mod x under root x square minus 1. And this result will be valid for mod x greater than 1. Domain of secant inverse x is mod x greater than equal to 1. But this differentiation is valid only for mod x greater than 1. This result is valid only for this. You must note this. Because y belongs to this, y is not equal to 0 or pi. Y is not equal to 0 pi means x is not equal to 1 or minus 1. So these 2 points must be deleted. So this is the differentiation of secant inverse x. On similar lines, you can try the differentiation of cosecant inverse x. Differentiation of cosecant inverse x will be minus 1 over mod x under root x square minus 1. You can try it yourself. I am now proceeding on to questions. First, I will prepare a list of formulae for inverse trigonometrical functions, and then we will take up some questions. Now, d by dx of sine inverse x is 1 over under root 1 minus x square. We have proved this result. And d by dx of cos inverse x is minus of this. As an aid to memory, we know sine inverse x plus cos inverse x is equal to pi by 2. And differentiating this, we have d by dx of sine inverse x plus d by dx of cos inverse x, and d by dx of pi by 2 is 0. And this implies d by dx of cos inverse x is equal to minus d by dx of sine inverse x. So d by dx of cos inverse x minus d by dx of sine inverse x. And similarly, tan inverse x plus cot inverse x is pi by 2, and therefore d by dx of tan inverse x plus d by dx of cot inverse x must be equal to 0, and therefore d by dx of cot inverse x is equal to minus tan inverse x. And similarly, for secant and cosecant, we have d by dx of cosecant inverse x is minus d by dx of secant inverse x. d by dx of cosecant inverse x is minus d by dx of secant inverse x. And you can memorize these results.